Uh, All right, so I will get started with the material. And hopefully these first couple of sections are review. Stuff that you saw in Calc 1. But it's good to have a refresher before we get too far into things. So if you took Calc 1 here, you actually went through all of chapter 5 and did even a couple of sections of chapter 6. But I wanted to get a little bit of a refresher, just so we get back in the groove of hitting antiderivatives, because all of the chapter 6 stuff that we're gonna be working with has this as an underpinning. Okay, so back in section 5.1, we were looking at taking antiderivatives. So what that means is we're reversing the concept of taking a derivative. So if I knew I have this function and I know the function's derivative, f prime of x, is 2x plus 3, what could the original function be? Now, the big idea is that there's actually lots of functions that work. There's a whole class of functions that work. If we set f of x to be x squared plus 3x, then the derivative would be what we want. Then the derivative would be 2x plus 3. You guys remember taking derivatives, exponent comes on a polynomial, exponent comes down in front, and then it gets lowered by 1. So exponent of 2 comes down, multiplies the coefficient of 1, and then that x squared becomes an x to the first. And then this x to the first becomes an x to the 0, which is just a 1, which we don't have to write. However, we also saw that the derivative of a constant number is 0. So anytime we want to add a constant number to that, like we add 5 to my original function, or we subtract 7 from my original function, that's going to give us the same derivative. So x squared plus 3x plus 5 also gives the same derivative. And x squared plus 3x minus 7 also gives the same derivative. All right. So yes, there are lots of functions that work, but they're all different by just a constant. So we usually add on variable c as our constant. When you write the plus c into Moodle, that c will want to be capitalized. All right, so you want to write a plus capital C. If you do a lowercase, sometimes Moodle understands that, sometimes it doesn't. So when you write answers into Moodle and it has a plus C on it, make sure that plus C is capital C. Okay. So the concept of the antiderivative is essentially just that. We start with a function and we say, what function could I take a derivative of and get the thing I'm given. All right, so I have to reverse the derivative process. And the notation for that is an indefinite integral. This indefinite integral is asking for all of the antiderivatives. It's asking you to find the antiderivative with the plus c in. Okay, so your whole class of antiderivatives. So an antiderivative is a particular function that gives you the correct derivative. The indefinite integral is the class of all antiderivatives. So you do the plus c on that.
Could you go back?
Yep.
Thank you.
So in terms of the big idea of finding the function whose derivative is the function that you're given. Okay, in terms of the big idea, that's what we're doing. And the way this works out, anytime I'm given an indefinite integral, my answer is going to be looking like f of x, some function, and then I'm gonna have to tack on a plus c at the end. All right, so that it gives us all antiderivatives. Usually, the capital F of x that we use, we say, well, let's let the constant be 0, and so plus c at the end. Most people don't do a, plus 3 and then also plus c. Because if you did a plus 3, let's say we had x squared plus 3x plus 4 plus c. If I had x squared plus 3x plus 4 plus c, that 4 and the plus c could get sort of absorbed together. And that would all just be a single constant number of c. So usually when we write the indefinite integral, you won't have a plus 4 plus c, you just have a plus c. Does that make sense? Maybe this one. See if I can get it. Right. So yeah, so that's my indefinite integral of 2x plus 3 with respect to x. Indefinite integral of 2x plus 3 with respect to x. That's what that is thinking. I didn't rewrite that. Right, so we usually don't add a constant there. Oftentimes also, people put parentheses around that so that you can see the function that we're integrating is 2x plus 3. This dx just means we're integrating that with respect to x, meaning x is the variable in here. Because you can integrate with respect to other variables if you have lots of different variables in your function. Okay, so that's it. Oftentimes when we're only dealing with x, some people leave the dx off. But you should have the dx on. Oh. Technically. All right. So that's the deal. Now, what we're gonna do is we're going to look and calculate various indefinite integrals. So let's take the indefinite integral x to the fourth plus 3x and integrate that with respect to x. And then I will also take the indefinite integral 4x plus cosine of x and integrate that with respect to x. Okay. So here are two different functions where we'll find the indefinite integral. You guys remember the techniques of finding antiderivative? For the polynomial pieces, like x to the fourth and 3x, if the derivative makes the exponent come out front and multiply, and then it reduces the exponent by 1, the antiderivative increases the exponent by 1. And then instead of multiplying, you're going to be dividing by your new exponent. So we had a implied 1 as a coefficient. So we add 1 to the exponent and then divide by that new exponent. Divide the coefficient by the new exponent. So here, this is 3x. That's an implied x to the first. So if I increase the exponent by 1, I'm going to get an x squared. My coefficient is 3/2. And then, as always, I need to take a plus c with it. Now, if we have a function like 4x plus cosine of x, where one of the individual terms is a polynomial term, I can use the same technique on the polynomial term individually, as long as it's separated by plus minus. So that's why I say term, right? If this was 4x times cosine x, it'd be different. But 4x is its own term, cosine x is its own term. So I can do the same thing I did over there on the 4x component, that term, increase the exponent by 1, you get x squared, and then you divide the coefficient by 2. So 4 divided by 2 is your new coefficient. For the cosine, we think of what trig function has a derivative that's cosine. And that's sine, right? So the antiderivative of cosine is going to be sine of x. Now, I believe in Moodle, you can actually write 4 divided by 2, and it's equivalent. I don't think it requires you every time to reduce these, but oftentimes on the board, and just in normal life, when we can reduce fractions, I tend to reduce fractions. And a lot of times I'll just do that in my head. I'll just say 4/2, make it a 2. Right? So it's not necessary all the time in Moodle to reduce fractions, but I like to reduce fractions, and so I do that on the board. Does that make sense? And hopefully, we remember some of our rules for integration. Again, most of this is gonna be review, if you took Calc 1. So I'll go through these very quickly. We've already kind of used these already. If I have some coefficient in front of a function, I just think of it as integrate the function and pull the coefficient on the outside. So when I integrated 3x to the first, I could think of, well, how do I integrate x to the first? And I can just keep the 3 on the outside, right? And say divide by x squared, then divide by 2. Another rule for integration is if you have two functions that are added together, I can integrate them separately. I can integrate the first term or the first function, and then I can integrate the second function. We did that on both of the previous problems. When we did x to the fourth plus 3x to the first, I integrated the x to the fourth part, and then I integrated the 3x to the first part. When I integrated the 4x plus cosine of x, I integrated the 4x part, and then I integrated the cosine x part. Okay. And then lastly, anytime you're integrating 0, you have to have a constant, so that's the thing that's forcing us to do the plus c on the end of everything. Okay. One of the big rules for integration that, again, we just used was that when we have x to a power, like x to the fourth, or 4 times x to the first power, or 3 times x to the first power, the way to integrate that is to add 1 to the exponent. So x to the fourth became x to the fifth. And then divide the coefficient by the new exponent. And then obviously we always have to tack on that plus c. Now that works for any n possible, even if the n is not an integer. So if n was negative 3.8, you could actually apply that rule to x to the negative 3.8 power. The only place it doesn't work is when n is -1, because when n is -1, then you're dividing by 0 here. So that rule works for every n except when we have to divide by 0. And we divide by 0 when n is -1. So that rule works everywhere except when n is -1. And when n is -1, x to the -1 is the same thing as 1 over x. So when x is -1, we have to integrate 1 over x. And I hope that in Calc 1, people showed you that the derivative of natural log is 1 over x. Therefore, the antiderivative of 1 over x is natural log. Natural log only takes positive inputs, so that's why oftentimes people put absolute values around the x. In this class, when you're typing it into Moodle, you can just put parentheses around the x and it'll be fine. Is that right? When you type it in Moodle, don't worry about absolute values, just put parentheses around it. Be all right. We'll assume we all know it. Natural log only takes positive values. Here's some other ones. If you have e, the numerical value of e, 2.71828, right, that one, to a power, so e to some power, and that power is just a number times x. And I want to find the indefinite integral of e to a number times x. I take e to that same exact power, e to the ax, and then I divide by a. Divide the coefficient, that is, by a. And if you have another base, well, let me restate this. Move this up real quick. So this rule over here that I just wrote on the overhead, that comes from the fact that when you take e to the ax, or excuse me, just e to the x, the antiderivative of e to the x is e to the x, obviously plus c. The derivative of e to the x is e to the x. It's the function where when you take the derivative, it stays the same, right? E is this special number where you get this. If you took another number, okay, another number to the x power, it kind of does the same thing, but I have to adjust it by a coefficient. And that coefficient is 1 divided by the natural log of that base. So that's what is going on there. That's why I'm writing the rule as I just did. So e to the x, when you take the antiderivative, gives you e to the x plus c. But if you take a different base, you get that base to the x power, but you have to divide by 1 over natural log of the base. Notice that if a were e, these two rules are the same when a is e. Because if you take and I apply this rule to it, I get natural log of e times e to the x plus c, but 1 over natural log of e. Natural log of e is just the number 1. So that's 1 over 1, which is 1. And you get 1 times e to the x plus c. So those two rules are the same when you get base e. That's why base e is like a really nice base to work with these exponential functions. All right. So that's just another rule. I wanted to explain why that was up there on the board. That's one that we're gonna use a lot, by the way, these types of exponents, all that stuff. Another few rules. These are just applying to trig functions. And if you remember, the derivative of sine is cosine. So when you want to reverse that, when you want to take the antiderivative of cosine, you get sine plus c. We did that one already. The derivative of cosine is negative sine. So that means if we want to do the antiderivative of sine, I have to do negative cosine plus c. The derivative of tangent is secant squared. So that means if you integrate secant squared with respect to x, you get back tangent plus c. So those are basic trig integration things that we're going to use all semester. Okay. Here's ones that we don't use as much, but we will use some. If you want to integrate, well, let me rephrase this. The derivative of secant is secant tangent. So if you want to take the antiderivative of secant times tangent with respect to x, you get back secant plus c. The derivative of cosecant of x is negative cosecant times cotangent. So if you do antiderivative of cosecant times cotangent, you get negative cosecant plus c. And then if you take the derivative of cotangent, you get negative cosecant squared. So if you take the antiderivative of cosecant squared, you get negative cotangent plus c. So those six, the last six rules for integration, those are all basic takeaways from knowing the derivatives of our six trig functions. So if you know the derivatives of the six trig functions, then you can find the antiderivatives listed there. So let's take a look at a couple of examples here. I won't spend crazy amounts of time, but I will do these. 18x squared minus 5 with respect to x. And then 4 over x to the third with respect to x. I'll skip that one. Then let's also do 6 times e to the 2x and 7 over x. Okay, trying to write these down. 6. Great. Right, probably that very well. Again, hopefully this is review, so it's not too crazy. Skip some of the problems, skipped a couple of problems in there. Be okay with that? All right. So this first one, a 18x squared minus 5, I'm gonna find the antiderivative of that. So I focus on this first term, 18x squared. That's polynomial, so x gets raised to the third power. The 18 gets divided by 3. When the 18 got divided by 3, you could have said that's just going to be a 6. 18 over 3 is 6. And this 5, this minus 5, my other term, what is that going to turn into?
-5x.
Negative 5x, good. Negative 5x. Remember, when it's a constant, you can think of it as x to the 0 power. And if I raise 0 power by 1, you get x to the first. Dividing by 1 doesn't change anything. So you can think of that as x to the 0 power when you're dealing with constants. So there we go. Add a plus c, and we're done. Now, if you get into a situation like this, where we have 4 over x to the third, I want to point out that's different than 7 over x. This is 7 over x to the first, right? And if I were to rewrite 7 over x to the first, it would be 7 times x to the negative 1. Negative 1 is the case where I cannot use what I call the polynomial rule of integration. It was more broad than that, but x to a power rule. Here, I can rewrite this one as 4x to the negative third. Then I can use the x to a power rule. Again, sometimes it's not precise language, but I improperly will say, oh, that's the polynomial rule, because that's the rule you use always with polynomials. But it also works with stuff like this, which is not a polynomial. So the x to a power rule says, I'm going to increase that exponent by 1. So negative 3 plus 1 becomes a negative 2. And then I'm going to divide by my new exponent, which is a negative 2. So I'm going to take 4 divided by negative 2. So you end up with negative 2 times x to the negative 2 power plus c, using the x to a power rule. Sometimes people like to rewrite this x to the negative 2 in a numerator is like x to the positive 2 in the denominator. So sometimes people will write that with positive exponents. Sometimes people will leave it with negative exponents. I'm not going to care which one you utilize. I think Moodle should interpret these as the same. Okay. Should interpret those as the same. And if it doesn't, obviously let me know. So you'll notice that in this case, I had to rewrite it and then and then integrate. Okay. By the way, when you just rewrite something, keep the integration symbol and the dx. Some people will rewrite it and forget to write the integration symbol because they're so used to going from function to antiderivative. So keep that integration symbol if you're just rewriting. And then drop it when you do the antiderivative or when you integrate. All right, let's take a look at this. This was our e to the power rule. So I'm going to take e to that same power. And then because we have a 2x, I'm going to take the 6 as my coefficient and divide by 2. So when I'm dealing with exponential functions, which have linear exponents, that's the way I deal with those. So exponential functions with linear exponents. Last problem on these examples, if I try to do it the same way as 4x to the negative 3, I'm going to get a problem because it's going to say add 1 and I get a 0, then I have to divide by 0. So this is the case when we have x to the first power in the denominator where we use natural log. Now be careful, this 7 is just a number that I could technically just pull out. I could make this 7 times integrate 1 over x dx, because remember we can pull constant multiples out. 1 over x integrates as natural log, so we get 7 times the natural log of x plus c. And that's it. That's the whole thing. Notice that I put parentheses around the x. In the back of my mind, I know that natural log can only accept positive values. Again, I hope this is refresher for you. Hope this isn't too crazy. Just practice on taking antiderivatives. Okay. Let's do this one. Cosine of x minus secant squared. Of x. Integrate that whole thing with respect to x. So when we integrate the cosine piece, so let me step back for a second. We have two terms here separated by the minus sign. So we're going to integrate each one individually. And these are both trig functions. So we're going to scroll back to where we had our trig functions. And it says if I want to integrate cosine, I can make it, the antiderivative is going to be sine. At least one antiderivative is going to be sine. And if I want to integrate secant squared, then one antiderivative is going to be tangent. So when I have something like cosine minus secant squared that I'm taking the antiderivative of, the cosine piece has antiderivative of sine x. Secant has antiderivative of tangent of x. And then I can just put 1 plus c at the end. Right? All constant new numbers, all constant terms can be absorbed by just a single plus c. that work? Not too crazy. I got flip forward because I flip back. I'll leave that. Oh, shoot, that was not, thought that was protected. Now, I don't know how much of this you did in Calc 1. Depending on your Calc 1 class, you might have and you might not have done finding a specific antiderivative given some initial known value. So we've been integrating and we've been putting this plus c at the end. Well, what I can do if I want to is if I know some initial condition, I can find the plus c as well. I can find which c to use. So for instance, let's say I want to find the antiderivative of 6x squared plus 8 if I know the antiderivative goes through the point 217. And then I'll find the antiderivative of 6x squared plus 8 if I know the antiderivative goes through the point 248. So we need to find the antiderivative of f of x equals 6x squared plus 8 that goes through to 17. I'll write that on the board. And I'll find the antiderivative that goes to the point 248 as well. Again, I don't know how much of this you did and how much you didn't do in Calc 1. This is not a lot of it, but if you do want to find a specific antiderivative and not a whole class of antiderivatives, then all we have to do is start out by integrating our function. In this case, it's 6x squared plus 8. So when you take the antiderivative, you end up with 2x to the third plus 8x plus c. That means that the antiderivative that I'm looking for, I'll call it capital F of x. Is that okay? Just so it's different than lowercase. The one that I'm looking for needs to look like that. And moreover, it needs to go through the point 217. That means if you plug in the 2 in for the x, the output needs to be 17. So going through 217 means that if I plug in 2 for my input, I get an output That is 17. Notice what that does. That gives me an equation in which I can find what constant that I want for this particular case. Right? This is the output. Here's your inputs, right? X is your input. 17 is your output. So let me grab my calculator. 2 times 2 to the third is 16 plus 16, I get 32, I think. 17 plus 32 plus C. And then subtracting 32 from both sides. Gives me a constant that is a negative 15. Everybody following this? And that means that my function that the particular antiderivative that I am looking for needs to be 2x to the third plus 8x minus 15. So the particular one that I'm looking for needs to be that. Can you see that? I don't know if I just too low.
Yeah,
Okay.
thank you.
Now, if I know it's going through the point 248, it's the same process. I'm gonna antiderivative 6x squared plus 8 and find that, get the exact same thing. So my f of x needs to be 2x to the third, my capital F of x needs to be 2x to the third plus 8x plus some constant. In this case, if I know it goes through the point 248, I'm going to get a different antiderivative, right? My output is 48 this time when my input is 2. All of that's the same. Subtracting 32 from both sides. Gives me a constant that should be 16 in this case. Therefore, the particular antiderivative that I'm looking for is 2x to the third plus 8x plus 16. So if you do want to find a particular antiderivative, you can do that by figuring out what you get for the indefinite integral. And then if you have another piece of information, like a point that it goes through, you can use that point to find which constant we need. Yeah.
So when it's going through a point, that's different than a definite integral?
Yes, yeah, so this is saying we want to find a function which goes through a particular point. A definite integral, which is what we're going to do in 5.2, and 5, 4, I believe. That is asking you, what is the area under the curve? So this is asking for the function that is the antiderivative function that goes through a specific point, and a definite integral is asking you for an area under the curve.
Thank you.
Yeah. All right. Now, I don't do a lot of these. I don't do a lot of, let's find the particular antiderivative. So I'm not gonna spend a lot of time doing that. So we'll leave 5,1 right there. Okay, so that'll be the end of section 5,1. And we'll go right into what we we're just mentioning, which is the definite integral. Section 5,2. Now, the big idea of the definite integral is it calculates signed area. Normally, when we say the area under the curve, we imagine our function be positive. So it's above the x-axis. And if our curve is above the x-axis, the area between the curve and the x-axis is counted as a positive area. However, if our area is below the x-axis, then the area between the x-axis and the curve is counted as a negative. Does that make sense? So we want to calculate signed area. So if you look at this, if I say, let's let this line be the curve that I'm looking at from 0 all the way up to 6. Because this line is above the x-axis, this area, whoops, is going to be counted as a positive. Does that make sense? And by the way, in this case, you could use some calculus to do it. Or in this case, you can just say that's a triangle and you can calculate the area of that triangle. 1/2 base times height. What would that be? 6 times 3, 1/2, 6 times 3, you get a 9. So the area should be 9. And it's a positive 9 because our curve is above the x-axis. That area is above the x-axis. If you figured out, or if you looked at a picture like this, we have 2 triangles. One that is above the x-axis and one that's below the x-axis. In calculus, if you look at the line, starting at the point 0, 2 and going all the way to the point 6, -1, that would be the line that we're looking at when eventually we'll take a definite integral. Okay, we'll take the definite integral of that line. But if you look at the area between the x-axis and that line, some of the area is positive, some of the area is negative. The area above the x-axis over here is positive. The area below the x-axis is negative. So if you calculated that area of the first triangle, that would be, again, 1/2 base times height. Base is 4, height is 2. So that's area of the first triangle, the positive area. Would be 4. The area of this other triangle, well, base here is 2, height is 1. 1/2 base times height gives you an area of 1, right? But because it's below the x-axis, it's counted as -1. So when we do our calculation of area, of signed area, I'm gonna have to take the area of 4 and subtract 1 from it. So the +4 plus a -1. And so the signed area of this figure in total would be a +3. Does that make sense? So that's what we mean by signed area. I just did that with, by the way, this signed area, because the bigger triangle is underneath, this signed area would be a negative area, right? If you put the entire thing together. Okay. So the big idea of definite integrals is that we want to calculate that signed area. We want to calculate the area between the function and the x-axis. And if the function is above the x-axis, that area is going to be counted as positive. If the function is below the x-axis, it's going to be counted as negative. And if it's partially above, pieces that are above are going to be counted as positive, and partially below, pieces that are below are going to be counted as negative. That's the big idea. And it turns out, no matter what the function is, as long as we can integrate it, there's this thing called the definite integral. The definite integral is the integration of a function f of x with respect to x from a to b, meaning from the x value, which starts at a and ending at an x value, ending at b. So the a and the b are known as the bounds of the integration. And this definite integral gives you the signed area underneath f between x values of a and b. And the nice thing about it, well, there's a bunch of stuff that's nice. One nice thing about this is if your function, you want to break it up into pieces, you can break it up into pieces. Like if you want to do the first triangle that's above the x-axis and the second triangle that's below the x-axis, you could add those two signed areas together. Or you can do a definite integral from the very start to the very end, and that'll work too. So that's one nice thing. That the definite integral you can break into pieces if you want. Oh, crap. Oh, that was just geometry stuff? Correct. Okay. I forgot, that's in 4. So. What we've done so far is we looked at integrations, definite integrals on triangles, right? With all of our little pictures above and below being straight lines. And if we have triangles, we can do it using geometry. We can say, oh, that triangle is this thing. That triangle has area 4. This other triangle has area -1. Or this triangle has area 3, and this other one has area 5. So anytime I can break up my picture into nice triangles and rectangles, I can do that. And if you're ever integrating a straight line, you can break it up into triangles and rectangles. Okay. But if you want to find the area underneath x squared plus x from 1 to 4, that's going to be really hard to break up into rectangular pieces and triangular pieces. So let me do something online to explain this. So let's take 2x minus 1 from 1 to 4. Now I'm going to look at this graphically. So I'm going to look up an online calculator called Desmos. I logged in there. There we go. There you go. So I'm logged in. And this is free, open source calculator. Let's take f of x equals 2x, I think it was 2x minus 1. And I'm going to look at the area from 1 to 4. Now, one of the ways you can do the area from 1 to 4 is say x value between 1 and 4. Let's do a less than or equals. Greater than or. Okay, so here's the section of that line I'm looking under. Okay. So let's try to figure out the area here. Actually, let me do this way. Since that's above the x-axis, it's going to be this area. Are you okay with that? If you look at this area, this is basically a triangle along with a little rectangle. And so you could use geometry to say, well, what's the area of this rectangle? What's the area of this big triangle? Add them together and get an area. So that's a nice thing, right? So I could find the area under that curve, the signed area under that curve, using geometry if I wanted to. The trouble with that is that when we have something like x squared minus x, and I'm going to make sure that that was the example that was there, x squared plus x, excuse me, x squared plus x. from 1 to 4. Even though this little curve looks fairly triangular, it's not a triangle. This has a little bit, it's not a straight line. Okay? And so if I want to find this area, I can't really do it effectively using geometry because this section is not a straight line. So it's not going to be a normal geometry forming, right? And so this is where you turn to the calculus stuff. You can calculate using geometry if you want, if everything's nice straight lines. So that's my point. If everything has nice straight lines, like we did with 2x plus 1 or 2x minus 1, then geometry works great. If we don't have nice straight lines, and I don't know sort of the curvature of this, in fact, the curvature kind of changes as you move along this, then we're going to have a harder time. And that's where the calculus comes in. And that's where we apply the tools of integration along with this definite integral. All right. Now, most of that we'll do next class period. But I did want to just say this. Just a note on definite integrals before we start doing definite integral calculations next class period. So definite integrals gives us the signed area. But it gives us the signed area the way I told you, as long as A is smaller than B. So if you write this in the usual way, you write your smaller number underneath and your bigger number above. If somebody gives you a definite integral that switches that, where they write the smaller number above and the bigger number below, then you have to realize it gives you the negative of the signed area that we've talked about. So flipping the above bound and the below bound gives you the negative of the signed area that you're looking for. Does that make sense? So be careful about that if you're calculating signed area, and if you flip those bounds, it's gonna negate everything. So things that were above the x-axis now get calculated as a negative, and below now would get calculated as a positive. Whereas the usual understanding of signed area is above gets counted as positive, below gets counted as negative. Does that work? All right. So next time, we're done with 5.1 and 5.2. You can start those homeworks if you'd like. Next time, we're going to go into 5.4. And if you don't want to use geometry to solve some of the homework problems in 5.2, you can wait till next class period and we can solve those same problems with calculus. Does that work? All right. So that is it for today, and I'll see you next time.